Excellent. Let me move these distractions off to the side. First of all, thank you to Gordon and all the other organizers of ACAT for inviting me to speak. I'm very sorry I can't be there in person. Normally I would just have to come across the water and drive over for a few minutes, but I had to be in Kentucky today, and I swear it was not to see the eclipse, although that happened too, just about a half an hour ago here. I'm going to be talking about ways that we are trying to make C++ more powerful and simpler with an example that I hope will appeal to your particular domain, although it's a general, very horizontal approach that is aiming to make C++ both more powerful and simpler. But since this is the Advanced Computing and Analysis Techniques in Physics Research workshop, I thought I would start off with why simplicity could be useful. And let me just switch to a video I took half an hour ago. And I'm curious, I don't know if I'll be able to hear your answers, but can anyone in the room tell me what we're looking at? I took a video under trees about a half an hour ago.
So this is the sun when it's being partially blocked by the moon. You have a sort of a little pinhole, so you see actually the shape of the sun.
Exactly. So nature's pinhole camera. So the leaves happen to make little pinholes. I did not know this happened until about half an hour ago. But when I observed it, I was quite proud of myself that I figured out what it likely was, and the internet confirmed it. So of course it must be true. But thank you for now actually confirming that. But it's remarkable because here we have a not very advanced computing device, a not very advanced analysis, and yet that accomplishes a goal quite well. And I think there's some parallel in that with what we're trying to accomplish for C++. Sometimes just a few simple tricks go a long way. So let me give you an idea of what we're trying to do. None of this is going to be immediately in the next standard of C++ or anything like that, but this is something that we're currently working on that may be of interest as you use C++, especially for high performance and data-driven kinds of applications. So there's a movie in theaters right now, and it's actually not this one. I'll modify this recent movie poster just a little bit. And the point here is that when Bjarne Stroustrup invented C++, he did something, and he's very important, and he stuck to his guns. He had a unified type system. So in our programming language, there is no distinction between an object type and a value type. There is no distinction between a single inheritance-based class and a multiple inheritance-based class. We also can express many other things like COM classes, Corba interfaces, pod values, traits types, iterators, enums, all sorts of things, some of which weren't known at the time that Bjarne invented the language, such as expression templates, and properties have become popular. We've recently standardized variants and any. Every single one of these is just a class in C++. And that is a very powerful thing. Bjarne, for about 30 years, has resisted, by his account, hundreds of people, possibly thousands, asking him to bifurcate the type system, to make a struct not be the same thing as a class, except syntactically in the language. But they are the same. This is incredibly important, and it's the basis for a simplification. So the point of this slide is we already express all these rich types today all as C++ classes, using the same class under the covers. It's just that we write them by convention, and we describe those conventions in English instead of code. For example, a functor is a type that overloads the function call operator paren. A container is a type that has .begin that returns an iterator and that has pushback that takes a value. Oh, and by the way, an iterator is something that you can ++ and sometimes -- if it's bidirectional, that you can dereference to get access. So all of these have conventions. The ones in the standard are written as English tables of what this type must do. But wouldn't it be better to express it as code? And so the goal of this project in a nutshell is to assume that C++ gets strong compile-time programming and strong compile-time reflection. I'm not going to talk about those much. I'm just going to assume they exist, and those are being in the process of being standardized right now in alignment with this proposal that builds on them. And I want to use that compile-time code that is coming to C++ in the near future to actually give a name to an iterator and what that means as code, to a COM class, what that means as code, a pod value. And each one of those is a subset of this universe of classes, because all of them are just a class, but it's a subset that has common characteristics, and I want to be able to nail a name onto as a programmer and then use that name as a word of power. I want to express that subset using compile time code, and that lets me do something that we can't do today in C++, not even with concepts, if you're familiar with that new C++ feature, which is about querying types. This would let you actually say, I want to author a type that's an iterator, and get defaults right, get constraints enforced at compile time, instead of having it be by convention. So I'll give you, in this 25 minutes that we have, a very brief overview, and at the end an example that, thanks to a couple of the people, I believe in your audience and researchers at CERN, who have taken a domain-specific example that they're used to show how this approach can help with that. The most important thing to understand, if you know C++, you know that when you write the source code on the left-hand side of the screen, what you actually get is much more. For example, with class point on the left-hand side, every seasoned C++ programmer just knows that, oh, X and Y are private, and oh, by the way, I get a default construction, default copy construction and assignment, default move construction and assignment, a default no except now since C++11 destructor. But I didn't have to write any of that. It's just implicit in the language. And then when I, in the lower left, inherit from a base class, well, if I wrote a function void f that happens to be the signature of a function in the base class, guess what? If that's virtual in the base class, it's also implicitly virtual in my class. And here also my access is implicitly public because I wrote struct. So these rules are hardwired into the language standard as English-like standardese. And you might think of it kind of like this pseudocode. The compiler is basically saying, okay, for each member, if you didn't specify access, then if this is a class, I'll make it private by default, otherwise public. And oh, for every function, if there's a virtual one of these in the base class, and I didn't say virtual on this one, guess what? It's implicitly virtual. And if it's not virtual in the base class, but I said override in my derived class, then I would give a compile time error. Hey, you said I'm explicitly overriding a base virtual function. This is not a virtual function in the base class, and so forth. And all these rules are expressed as standardese. They're not expressed as this middle pseudocode. The goal of my project is to write almost exactly that pseudocode as real C++ compile time code, and let you write it yourself, so that we can not only implement, if we wanted to in the future, the things the standard already expresses in English this way, but that you can write your own kinds of classes and categories. So that's the mental model. What if you could write your own code here that runs at compile time during compilation, and basically attach a name to a group of types that they're still, when all said and done, they're still just a class that's generated, but they have a common set of defaults and enforced constraints and behaviors. And the nice thing about this code you write in the middle is just ordinary code, although it's compile time, and just like code, you can put it in namespaces, share it as a library on GitHub, and all of those things. So just to put some bounds on what we're doing and not doing, nothing too crazy. We're providing this one hook in the middle as an extensibility point. We are not making the language grammar mutable. It would be crazy, at least right now, and I don't need it for this purpose, to suddenly have a mutable language. I still want to know what my source code means. I just want to be able to supply some rules and defaults, and being able to customize that middle column already gives me plenty and way more than some might be comfortable with of customization. We're not doing anything to customize the language grammar. It's rich enough. Nor are we doing anything to change the definitions that are generated from the source code. Once they're generated, everybody agrees what they are. You can't change the definition of a class after the fact. All we're doing is saying what you write in source, hey, look, the class that we generate, just like the class and struct keywords do today to give you defaults and enforce rules, hey, we're just going to give you a way to write some of those nouns yourself. And so the idea is that, and all of the syntax is still experimental, is that you could write something like $class, so a meta class interface. And in there, you would somehow, I'll show you on the next few slides, write the rules that say, hey, all your functions you write are public by default and pure virtual by default, and we're going to enforce you didn't write anything different, things like that. And then once you have this name, then to use it, and again, this syntax is malleable, but use it in the place of the generic class or struct when you define a type. So you could say, for instance, std experimental interface shape, and then write all your normal members like you normally would, but your functions would be public by default and pure virtual by default and be enforced that you didn't write something else. That's the idea. You can do a lot because this is code. As soon as you let people write code, you know, it's anything computable they can express. But the three biggest, most common uses that we expect are to enforce rules, so that the user stays within the bounds of what this category of type is expected to do, to provide defaults so that you don't have to write them yourself. Typically those go a lot with the rules, because if there's certain things that must be this way for a certain category of type, why make the programmer write them explicitly? They usually work well as defaults. And then to provide implicitly generated functions, like an interface should have a virtual destructor by default, things like that. So I'll show a couple of examples, and there are more in the paper P0707. You can find that on my blog, also herbsutter.com, in a very recent blog post in July. I believe still the most current blog post that has links to that and much more information. But let's just go through a couple of examples now. So I mentioned interface not because this is in any way attached to OO style programming. That's perfectly fine, but you don't have to do OO in C++. You can use templates and compile time polymorphism and anything else. But interface is something a lot of people understand because they know it from other languages. It's a very common idiom in C++. And the way you write it today on the left-hand side is you say class. So my class shape has all these public functions, and I write virtual and equals 0, so pure virtual. And I'm going to make that red because that's really boilerplate. It's what I need to do to write an interface, but it's just a ceremony that's required today in C++. I have to repeat those things. Oh, and I better not forget the virtual destructor. And then in the comments, I have to be careful not to unintentionally write a data member, because interfaces are supposed to be zero size, no data. I shouldn't write a copying function because that doesn't make sense for an interface. You should use a clone function instead. I shouldn't have a non-public function. And I can do all that today, but if I forget and I get it wrong and I do write it accidentally, it compiles as if nothing was wrong at all. And I've accidentally violated the contract I wanted to respect. And that can happen easily under maintenance, because maybe it's my future self 6 months from now, or the intern a year from now who's maintaining this and just throws in a member variable and it compiles and runs, but now it doesn't do what I intended and may violate assumptions elsewhere in the system. So under the proposal here, I could write just interface shape, and I can just write two functions. They're public by default. I didn't have to write public anywhere. They're pure virtual by default. I generate a virtual destructor by default, and I can enforce rules that there are no data members and no copying. And I'll demonstrate that in a moment, and hopefully this connection will let me do that with the screen sharing. So here is the implementation. The code that I'm proposing that you write in that middle piece between transforming the source into the actual AST, or the actual class that's generated by the compiler, looks something like this. And again, this is malleable syntax. But the idea is, if I write interface shape, then hey, look, I'm just going to declare a virtual destructor by default. It's going to be virtual because I'm going to now, in the next context per block, which is compile time code, going to make all the functions virtual, including that interface destructor that I just inserted. And there, in that context per block of code, you'll notice the first thing I do is I require, this is a hook into the compiler's error handling, I require that there are no data members in this interface. There should be no instance members. It should be zero-sized. And an empty base class is what it's intended to be. And if there are any, I'll emit the error using the compiler's own diagnostics. Hey, interfaces may not contain data members. If that succeeds, that interface variables is empty, then I'm going to go through this regular looking for loop. And notice when I say $interface in these two places, that's just reflecting over this type that I'm instantiating, that I'm defining. So I'm reflecting over myself. $interface, now let me reflect over its functions. And I'm going to require that for every function, first of all, I'm going to require it's not copy or move. And I'll give a helpful diagnostic. Hey, if you wrote something like that, you'll see the error. Interfaces may not copy or move. Consider a virtual clone. Then I'm going to make sure that if it doesn't have an access specifier, I'm going to make it public by default and then require that it's public, so that if the programmer wrote something like protected or private, they would get the error interface functions must be public. And then finally, I'll just force it to be pure virtual. And the idea is that then the user just writes the code in the bottom right of the screen, which is pretty much what we saw on the previous slide. And that program we just saw runs on the contents that the user puts between the braces of interface shape. They write 3 functions, and that loop will iterate over those 3 functions, make sure there's no copying or moving, make sure there's nothing private, there's no data, and those kinds of things. Now, it's interesting because if you look at this metacode that's on the main part of the screen, that's something like 10 lines of code. And it's interesting to compare that with what we do today. Today, we would write something like this as standardese. If we added this to the C++ standard as a feature, the normal way we would do it now is to add yet another built-in type like struct and class and union are, called interface. And we would write several pages of standardese. In fact, if you look at C#'s standard, which I'll show you in just a moment, it's 18 pages of standardese that would express those features, which are the same as I can just write in 10 lines of code here. Plus, the nice thing about code is I can test it. I can write unit tests for this code to make sure that it's applying the right defaults, that it's rejecting the right errors. And I can share this code on GitHub, which I can't do if I add this interface concept into the language the way struct and union are, where I have to wait for my compiler implementer to get around to implementing it and get a new version of the compiler before I can use it. Now, I make a claim on the right-hand side that the aim here is that there is no loss in usability, expressiveness, error quality, diagnostics, or performance, even compared to other languages that add this as a built-in feature. Now, that is a really high bar, so I feel the need to explain that a little. Obviously, performance, you'll probably believe me because this runs at compile time, so at least conceptually you can say, okay, there's no runtime overhead. I'm just manipulating the source to definition transformation. But once it's defined, it's just another class. And okay, so there should be no runtime performance overhead, and there isn't. But can I really get as high quality diagnostics? Can I really get the flexibility and usability compared to a language that builds this in? And again, I owe a huge debt here to Bjarne Strustrup for making there be just a class, that there is one universe of classes and not a bifurcated type system, because that is essential to making this work. So let me now, just for a moment, try to justify this claim on the right-hand side of the screen. I told you I'd show you the C# language. Here is a screenshot of the C# spec, the current C# spec. And if you look closely at high res, it's the interfaces section. And this is the specification in C#, which is basically identical, modulo a couple of very minor checks that we could also add, basically identical to the 10 lines of testable code on the right-hand side. I think that already is a fairly strong statement in terms of the generality and simplicity of what metaclasses let us express. But digging into this just a little bit more, if you compare the C# or Java code with what we would be able to write in C++, they differ by the semicolon at the end, because, well, this is C++, we inherited the C grammar, so we do semicolons, oh well. And we also have additional features like const, which is not a concept in C# or Java. But now let me try this, and hopefully this will work thanks to screen sharing, but I will actually go to C#. Here is an actual C# application open in Visual Studio. And I wrote interface shape, very similar to what we just saw here. In fact, I think it's identical, interface shape, with 2 functions, int area and void scale by a double. Now, Right now, it all compiles. You don't see any red squiggles. Let me just show you two things you might do that violate the rules of an interface and the error messages you get in C# today. So for instance, let's say we have a non-public function. So let's make this function private. Notice the red squiggles immediately go to area, and if we hover over that, it says, the modifier private is not valid for this item. Okay, so I can't say private, but could I maybe put in a data member of type int? Let me not indent. I don't want them to indent. It is far too helpful. Pardon me while I am OCD. If I put in the int I, now it's saying, oh, wait, you can't have a field or a data variable, an instance data variable, because interfaces can't contain data. All right, so we see how the language and compiler enforce those things. Now what I would like to show you is a prototype compiler that implements the code that I showed you. This is a Clang-based prototype by Andrew Sutton, so thank you very much, Andrew Sutton, for making this available. And here is basically the same code I just showed you, and then what I'm going to now do, and I also have a feature that debugs, that prints out at compile time what is generated. So let's just actually do something that is unthinkable. I am now going to take C# and paste it into C++. And that doesn't work, but you see why? It's a very simple reason. C++ requires a semicolon. If I add the semicolon, now this works. And notice here I'm using the compiler debug statement to print out what gets generated. So this is a contextual program that runs at compile time. And down below you can see in the lower right exactly what we would have written by hand today, but I wrote on line 22 interface I shape, and at the bottom I get virtual, pure virtual by default. I get a no except destructor by default. Now we talked about error messages. So if with C# we tried int I, remember we added data member, we say, oh, interfaces cannot contain fields. Let's try that here, int I, and now the live compiler will say, oh, error, interfaces may not contain data members, because that's the message that I wrote up here. And I can control the error message quality. So if instead we did the other thing we tried over here, which was we make a function non-public, which violates the rule that interfaces must contain only public member functions. Notice it says the modifier private is not valid for this item. Now, C#, the compiler writers could have given you a better error message here. They could have said interfaces must have only public functions. But when you're a compiler writer, you write generic messages sometimes, and you plug in the things that didn't match. In this case, this error message is very grammar-based. It's very much a compiler implementer's view of the world. This item can't have this modifier, and so they use a generic error message, which is fine. It's still correct. But if you do the same thing here with this interface, only private will have a colon, you get the message, error, interface functions must be public. I hope that is convincing about the claim 2 slides ago on the right, that we get not just the same runtime performance, but also competitive usability, expressiveness, and in this case, I would argue, in at least one of those two examples, a better diagnostic, even compared to a language that added it as a built-in feature. So now interface is just an example. You can write many of these yourself. Here's another one that we might standardize, which is a value type, or if you're a type theorist, a regular type. And instead of saying, okay, class point, here's my data, and then I have to reinstate the default constructor because I had another constructor, so it suppressed the compiler-generated one. Oh, by the way, I need comparisons as well. I could just write a meta class that says value, where data members are private by default, constructors or functions are public by default, and you always get a default constructor and comparison functions. You don't need to reinstate them. You don't actually need equals default or equals delete to override the generated functions anymore, because by opting into the meta class, you're saying exactly what you want. You want a type of this category. It has these behaviors, so of course you want them. There's no need to opt in or out. The reason that we have equals default and equals delete in the language today when applied to generated functions specifically is because right now we just have class instruct, which means we have one set of defaults for the entire universe of types, which is very diverse, and no one set of defaults can be right for everything. And that's why we need to have ways for the programmer to opt back in when the default was the heuristic guessed wrong and suppress the generated function, or to opt back out when the heuristic guessed wrong and added the generated function. Well, here we don't need that. You can still use equals delete for other reasons, such as to remove something from an overload set, but you don't need them to control generated functions because you have this word of power, value, that says exactly what you want. So think of it as a generalized opt-in where you can make this one word mean all of the opt-in that should apply to that class. And here is a sketch of how that value is created. And if you look at my blog post on herbsutter.com, you'll get a link to a live web compiler that will run this example, and you can play around with it and see how it works. So because we can't write all the things we want to write in C++ code, we've resorted across the industry to all sorts of custom ways to write these categories of classes. So in Windows world, we have COM, which has its own middle compiler, its idle language to describe the COM-like things we can't express in C++. And you have to compile your code two ways or maintain two pieces of code to describe the same object. Qt is a popular C++ framework that some of you may be familiar with that does much the same. They have the mock compiler, which goes through their header file with extensions that you compile both through the C++ compiler and through the mock compiler that generates more stuff, including metadata, that eventually runs through the C++ compiler. And we are currently in the process of validating over the coming months as a first step that metaclasses can potentially let us eliminate tools like the mock compiler and its language extensions entirely and get to the right-hand model, where we just compile C++. Furthermore, because you don't have that side compiler, Qt, the company, would not need to maintain it anymore. That's in their interest. Users wouldn't have to learn it anymore. Their build system gets simplified. And furthermore, the code that gets written is portable. It works with every compiler that supports the version of future C++ that has this feature, should it become standardized. So that is the goal. We'll see yet. We have lots of experiments to do to make sure that we can reach it and achieve it. It's not a this year or next year thing. But the goal is to have this simple compile model on the right in portable code on all compilers. And here's the example that, thank you to Axel Naumann and to Benedict Hegner in particular, who gave an example of how this feature of metaclasses could be used in the code that you folks write today, and Benedict in particular. So if you look at his pod.io, I think I'm pronouncing that correctly, his particle physics data models. Right now he has a YAML script with an example on the left-hand side of what you would write. And what this does is he runs it through a separate compiler, and it emits 5 C++ header files, one each for example hit, another for example hit collection, and then 3 more example hit const, example hit data, example hit obj, which are interrelated class types with all sorts of boilerplate. And the goal of this proposal is to be able to simply write, instead of in a separate file, in a separate script, and then run a separate compiler, simply say, hey, a pod.io data type can contain these things. For example, if you wanted, I'm not saying this is great design, but if you wanted, you could say, oh, any strings named description or author, they're const expr by default because their compile time, they don't actually appear in the generated code. They are for compile time use, so we can just make them const expr. Oh, and those doubles that you put in there, we'll just stick those into the same generated classes that are generated today, and the only distinction right now would be they would be in the same .h file instead of across .h files, but we would generate exactly the same during C++ compilation. And if we can achieve that, that would be a nice generalization and improvement over the complexity of many build tool chains that people use today, and template metaprogramming, macros, and all these other things we resort to, because we're already writing all these kinds of classes. We're just using them, writing them using difficult tools, by conventions in our heads, by conventions written in standardese, by conventions enforced by third-party languages and tools like IDLE or the mock compiler. And it would be nice if we could just write it all in C++. So you can think of this, the goal of this is expanding C++'s abstraction vocabulary beyond class, struct, union, and enum to be able to write your own word of power like that. You can use it for writing compile time-enforced coding standards. Another customer I was working with said they use a particular hardware interface library that requires classes to follow a certain pattern. You can codify that here and remove boilerplate and reduce errors by enforcing rules of compile time, and many other things. So users can write code and share it without waiting for a new compiler. In the standardization world, hopefully we could standardize more language features as libraries instead, which is easier to do and easier to test. And even C++ implementers can stop supporting over time, if this succeeds, as many of their proprietary tools and side compilers. So that's a quick overview of what we're trying to achieve, with at least an attempt to show how it would be applicable to the kinds of things that you do. And you know, as I was looking an hour ago and taking that video of the eclipse, it struck me how simple tools can go a long way. And so just like nature's pinhole camera is a useful tool, perhaps sometimes the solution is to have an advanced computing tool, an advanced technique that actually allows simpler code and that can shield the user from complexity. And that's the goal of this as one of several things I'm working on to make C++ more powerful still, do things we can't do today, but still make C++ code simpler. So thank you very much for your time and for the invitation. I'm happy to take questions.
Thank you for that nice talk. This is Gordon. Just two quick questions. First, can this meta class, can a single meta class generate multiple classes?
Yes, it can. The current prototype is one-for-one, but the prototype that's on the cppx.godbolt.org prototype compiler, the live compiler. But the one that we're actually working with this week can already do that, because you need to do that, for example, for things like Pod.io and for Qt, and also for Windows, for the C++ WinRT work that generates COM classes. You need to generate 4 or 5 different things for each of those. So the compiler that's on the web right now does not do that yet, but the next one that you'll see will, the one we're working with internally, already does that, and that is necessary.
Okay, and then the other quick question I had was, you said it depends on 2 other features of C++ which are not yet in the standard. I think one was reflection. I don't remember what the other one was. But
Sure.
What are the chances of those going in? Because I guess this doesn't make sense without that.
Right. So I'll say what they are, and the chances are high. They're well along. So they need compile time reflection, so you can reflect or inspect the kind of type you are and ask, iterate over your functions and inspect them and see what they are, that kind of thing. And then compile time programming and generation, so that you can do, like I was showing in those const extra blocks, write C++ code that runs at compile time, that does a for loop over those reflections to inspect each function, and also to generate things. So to some of the examples you'll see on my blog post that work on the live online compiler, that they show how you then will inject default functions. And so those 2 proposals are moving along very well. The reflection proposal is already moving along inside the main groups and standardization that's already received preliminary approval and is likely to become a technical specification in the next year or 2. And we're working closely with those authors. And basically, the syntax is just different that the user sees, but the engine is all the same. And we re-implemented it for this compiler, the same proposal. And the compile time programming is being done in coordination with this. So this is actually, the compiler for this work is also the prototype compiler for that proposal. If somebody else weren't making that proposal, I would have to propose it as part of this. I'm glad somebody else is proposing it so that we can each work on these 3 together. We just had our last standards meeting last month in Toronto, and the interest in the committee for all 3 of these parts was very strong. So that was encouraging.
Hi, Herb. This is Federico Carminati from CERN. I have two questions. The first one is, Björn Sostrup says that there is a very simple language inside C++ that is struggling to come out, and I see what you're doing as one more episode of this heroic struggle. And in some sense, you are moving complexity from somewhere else by abstracting it, and of course this reduces the overall complexity. I would like to know if you agree with this overall assumption, meaning that if I understood something what you said or not. And the second thing is that as a person who spends a lot of time in managing software packaging and so on, I see a little bit of danger, because if two different software packages, they meta-define interface or whatever in a different way, then you may have a major problem in putting them together.
Yes, so let me, Federico, thank you. So the simplicity is exactly a motivation of this. In fact, just between you and me and the doorpost, this grew through work of looking at what it would take to make C++ a 10x smaller language without losing expressiveness. And of that work, one of the major simplifications that I discovered was this. And so this is the first of those things I'm bringing to standardization. Having said that, it has great value on its own. And the thing to focus on is the things that lets us express, like the million things that lets us express in C++ that we can't do conveniently today. Having said that, you will no doubt notice that in the paper, many of the examples are other language features, including namespace, enum class, union, and if this were to go forward, you could imagine 5 or 10 years down the road entertaining the conversation of, you know what, do we really even need to have a separate namespace concept anymore? Because if you wrote the namespace metaclass, which is 5 lines of code in my paper, you would get not only all the value of namespaces, but more, because namespaces would naturally be able to do things that classes can do, such as have private data, instead of using the detail idiom, and then you're constantly jumping in and out of this detail namespace. But so yes, there's great opportunity for, and I hope that this can lead to simplifying the overall C++ language, because it gives us simpler ways to write things we already have. But it would be dangerous to focus too much on that, because the focus should be on the many things it lets us do that we can't do today, and that's where the immediate value is. As having two different people implement two different things, the short answer is yes, it's just like classes. If you were to show C++ to a C programmer, no doubt many did and would still say, oh, but if everybody can write their own string class, you'll have all these proliferated string classes, and that's absolutely true. And classes are still immensely valuable. What you do is you put them in namespaces, which you can do with metaclasses. Each library can have their own, and you can standardize in namespace STD the common ones like interface and value. So that would be the short answer. You do it like the same problem exists for classes, and you manage it the same way.
Hi, Herb. It's Axel. So I have
Hey,
a
Axel.
question. One of the problems we are having with C++ is debugging, especially with templates. That is not a lot of fun. Now, if you add this extra level of indirection to code, then of course debugging is going to be even more difficult. Now, I know what you're going to answer. You're going to say, well, I'm just designing the language here. The rest is just tooling issues, and those can be dealt with later. So let me just ask you the question. How would you see your ideal debugger behave with metaclasses?
So, Axel, that is the biggest question when it comes to implementing this. And I am happy to say that your expectation is wrong. I consider it essential that the designer of this answer that question, because if it's not usable, then I violated. Remember we said a few slides ago here, I made the claim, no loss in usability, diagnostics, that includes debuggability. So the good news is not only now can you, because this meta code is code that you can step into at compile time, so I expect debuggers to involve to allow you to step into compile time code, which we need anyway if we have compile time code even without metaclasses. We're going to need that. And really, we're doing it today. That's strictly better than what we have today with template metaprogramming, because compile time code lets us do much more directly what TMP merely approximates, never mind cough macros. And those are not debuggable at all. This is strictly better than that, and yes, we need the compile time debuggers. But more than that, if I go back to the example I showed, one of the reasons I showed this example, let me take the error away, and at the bottom right, you see the generated code. This is exactly what I expect tools to show you. You write what's in the middle right, interface shape. You can debug into and step into what is at the right bottom. That is exactly what I expect tools to do. Now, when you think about what that means today, think of going back to early on. This already exists today, this mapping from source code to definition. The right way to think about this is to say we already have this problem. Class and struct are just the first two meta classes, and their implementations are baked into the language spec and compilers. We already have the problem that for class point on the top left, if I step into the copy constructor, where the blazes do I go? And to the extent the tools already make that better, that same answer will work for meta classes. To the extent that meta classes get that support where we provide a way to see the generated result, because there is one deterministic generated result, and step into that, that will automatically make today's issue better with the code that we already have today that's shown on this screen to step into a generated function that we already have today. So I think that it's useful to think of class and struct, and also to an extent union and enum, as the first meta classes. All of those problems exist. They are absolutely important, but I think a key way to think of it is, if in doubt, try writing this compiler.debug statement. There is your beginning to what you should expect to see in next generation C++ tools if this continues, that you should just be able to see that and step into it, because you do want to know what's generated. You just don't want to have to write the code by hand yourself every time. Does that make sense?
Yes. Thanks.
Thank you all.